Hello students, welcome back. Today we are going to discuss the application of Gibbs-Duhem relation and into numerical problems regarding ideal gas mixing. We have seen the Gibbs-Duhem relations which basically connect the chemical potential to the composition of the system. And the problems that I am going to talk about today have been adopted from the classic physical chemistry textbook, which even I studied as a student when I was a young college student like you. And in today's class, we will look at the fundamental relationship that we obtained by starting from the Gibbs-Duhem relation before and after mixing of some ideal gases, and the result that I am going to use is the Gibbs energy of mixing at a given temperature and pressure, which is given by delta G mix, that is equal to nRT, then a summation over the terms x ln x corresponding to each of the components present in the mixture. Therefore, this is the working formula that one needs to remember when one is solving problems pertaining to thermodynamics of a mixture of m ideal gases. So, what is the important quantity that you need to know about the mixture? You need to know about what these quantities xi's are for the ith component in the ideal gas mixture. By definition, this is the mole fraction of the ith component in the ideal gas, and by Dalton's law of partial pressures, this mole fraction is related to the partial pressure of the ith component in the mixture, which is present at a total pressure of P. With this background, let me go ahead and try and look into a simple numerical problem which is stated as follows. Consider two pure gases A and B, each at 298 Kelvin and 1 atmospheric pressure. Determine the free energy of mixing of 10 moles of A and 10 moles of B at 298 K and 1 atmospheric pressure. So, we are looking at the mixing of two ideal gases. To start with, they were present in their pure phases. So, I had 10 moles of A in the pure phase, 10 moles of B in the pure phase under identical conditions of temperature and pressure. And then the final thermodynamic state is when these two gases have been mixed, and I want you to find out the free energy of mixing under the condition that there is no change in temperature and there is a constant total pressure of 1 atmosphere. The way I will solve it is obviously I will use this working formula. And as you understand that while using this working formula, I need to know what n is, what T is, and what the xi's are. I understand that I am working with a binary mixture. There are only two components A and B. Accordingly, I can write down delta mix G, that is equal to nRT xa ln xa plus xb ln xb, where xa and xb are the mole fractions of the gases A and B in the ideal gas mixture. So, in order to evaluate delta mix G, I need to find out what these xa and xb's are. By definition, of course, xi is equal to number of moles of the ith component in the mixture divided by the total number of moles n present in the ideal gas mixture. Now, let us go back and try to see there are 10 moles of A and 10 moles of B. Therefore, the total number of moles here n, that is given by 10 plus 10, that is 20 mole. Okay. So, what is Xa? I understand that Na is equal to 10 mole and this is equal to Nb. Therefore, I can quickly conclude that Xa is equal to Xb, that is equal to 10 mole divided by 20 mole, and that will give me that this is an equimolar mixture of A and B that I am talking about, and the mole fraction of each of the components is equal to 0.5. So, with this result, then you understand that it is now a trivial task to find out delta mix G. So, delta mix G is nRT into Xa plus Xb ln Xb. Now, obviously, I can write this for this mixture 2 times Xa ln Xa. Now, I know all the terms which appear here on the right hand side. So, what I will do is I will write down each of these quantities. So, N is 20 mole multiplied by R, that universal gas constant, which I know having the standard value. Then what is the temperature that I am talking about? 298 Kelvin, and then I have 2 multiplied by Xa is 0.5. So, 0.5 ln 0.5. So, what do you expect? You do expect a negative sign here. Why? Because I am taking the logarithm of a number which is less than 1, and sure enough delta G mix that turns out to be negative of 34.4 kilojoules. Therefore, in this particular problem, what we have done is we have taken this process, that in the initial equilibrium state I had 10 moles of the pure ideal gas A, and I also had 10 moles of pure ideal gas B separately maintained at 298 Kelvin and 1 atmospheric pressure. Then I allowed them to mix, leading to an equilibrium ideal gas mixture containing 10 moles of A and 10 moles of B. And I find that the free energy of mixing in this process is given by minus 34.4 kilojoules. Now, in many cases, whenever an examiner is setting the question, they would say, okay, there is nothing in this problem. It is just putting in the values and getting the answer. So, there can be an alternative statement trying to test if you have understood what this formula means. So, here is an alternative statement which is not exactly telling you that you have to find this delta G mix. So, it is the same first line. Consider 2 pure gases A and B, each at 298 Kelvin and 1 atmospheric pressure. Determine the Gibbs free energy of 10 moles of A and 10 moles of B relative to the unmixed gases. Okay, so, your formula that tells you that delta G mix is G of the mixture minus 10 moles of 10 moles multiplied by the molar Gibbs free energy of the component A minus 10 moles of the molar multiplied by the molar Gibbs free energy of the pure component B, right. So, I understand that if I look into this situation over here, what I have is delta G mix is G mixture, that is the absolute Gibbs free energy of the mixture, minus this is the absolute Gibbs free energy of the component A before mixing in its pure phase, and this is the contribution coming from the component B before mixing in its pure phase. So, if I look into the second equation here, I find that delta G mix or delta mix G, whichever way you prefer to call it, this is actually the difference between the Gibbs free energy of the mixture minus the Gibbs free energy of the unmixed gases. Therefore, if you just look at the statement of the problem, you were required to find out the Gibbs free energy of the mixture relative to the unmixed gases, and that is exactly what you have on the right hand side. So, essentially what is required is you are supposed to give the value of the quantity free energy of mixing. So, this is one very nice simple trick that you might encounter if you are writing an exam. Next, let us have some other problem, but related. So, I still have the same two pure gases A and B at the same temperature 298 Kelvin and 1 atmospheric pressure, but now I am asking you to find out the free energy of mixing of 10 moles of A and, unlike the problem before, 20 moles of B. So, once again I start by realizing that I have a binary mixture and I need to know XA and XB, and here I find that N total is 30 moles and Na is 10 mole and Nb is 20 mole. And then what I will do is I find that Xa is 1/3 and Xb is 2/3. So, the trick is very simple. I have a total of 30 moles at 298 Kelvin, and where in the mixture the first component mole fraction is 1/3 and the second component has a mole fraction of 2/3, and I can very easily put all these values in the expression and find out the corresponding free energy of mixing. And now it turns out to be minus 47.3 kilojoules per mole. So, what we have done is for this process where I had 10 moles of the pure ideal gas A and 20 moles of the pure ideal gas B, to produce the resultant ideal gas mixture, I find that the free energy of mixing is minus 47.3 kilojoule. Now, this is again a very straightforward problem. Now, what happens if I just change the problem a little bit? And the statement of this problem goes as follows. Calculate the change in Gibbs free energy if 10 moles of the ideal gas B are added to the mixture of 10 moles of A with 10 moles of B at 298 Kelvin and a total of 1 atmospheric pressure as before. So, now how is this problem different from the previous ones? Here you start with an ideal gas mixture which contains 10 moles of A and 10 moles of B, and to it you add 10 moles of a pure gas. So, in the initial equilibrium state you had an ideal gas mixture and you again had a pure gas. So, this is quite unlike what you had in the derivation of delta G mixing. Okay? And now I am producing an ideal gas mixture by mixing these two components. I am producing an ideal gas mixture which is comprised of 10 moles of A and 20 moles of B. So, I will call this as mixture 1, and this is being mixed with 10 moles of the pure ideal gas B, giving me the mixture 2. Okay? And I need to calculate the change in Gibbs free energy in this process. So, what is the change in Gibbs free energy? By definition, this must be G final minus G initial. So, what is G final? That is the free energy of mixture 2. So, that is what I have written here. This is minus G initial. In the G initial there are two parts, one is that of the mixture 1 and the other one is that of the pure gas B. So, G initial I have written as G mixture 1 and the other contribution is the G of 10 moles of the ideal gas B, and here that I write as 10 mole into G star MB, where G star is the molar Gibbs free energy for the pure ideal gas B, a notation that I have already used. Now, as you understand that there is no way I can directly evaluate delta G over here, but I know that from the formula, the working formula that I have, I can identify how to model this particular problem. So, I am looking at how I go from mixture 1 to mixture 2 by adding 10 moles of B. But I also know that how to produce mixture 1 from the ingredients, and I also know what is the corresponding mixing free energy. Similarly, for the mixture 2, I know how to create this ideal gas mixture starting from the scratch, and again I know delta mixing G2, and then I realize that for this process I can write down delta mix G1 as G mixture 1 minus 10 moles multiplied by the Gibbs free energy of the molar Gibbs free energy of the pure phase A minus molar Gibbs free energy of the pure phase B multiplied by 10. Similarly, I can write down a similar expression for the second mixture. Now, I am going to combine the two. When I combine the two, I write delta mix G2, this by definition is this, delta mix G1 by definition is this. Now, I am going to subtract the second equation from the first one. So, how do you do it? And in pen and paper, what you do is you change the signs over here and you write down the result. So, the first term that I get from the left hand side is the Gibbs free energy of mixing for the second mixture minus Gibbs free energy of mixing for the mixture 1. What do I get on the right hand side? I must be having G mixture 2 minus G mixture 1 from this these two terms. Then I find that these two terms cancel out and I am left with these two terms, which eventually gives me minus 10 mole multiplied by G star MB. Okay. So, if I go ahead and use this, I understand that there are some quantities that I know here. So, what is it that I know? This entire expression that I see here, this is equal to delta G. So, can I find out delta G by knowing these two free energy of mixing? The answer is yes, because I know that this quantity is minus 47.3 kilojoule and this quantity is minus 34.4 kilojoule. Therefore, it is a trivial task now to write down delta G as delta G mix G2 minus delta G mix G1, which now turns out to be minus 12.9 kilojoules. So, that tells you that not all problems can be solved by just plugging in values to a given working formula. You will have to think a little bit and then you will find how the working formula helps you to solve the problem if you have understood what that working formula means. Now, let us go ahead and try and have a look at some other problem. I want you to find out the free energy of mixing per mole in units of RT for a mixture of 4 moles of nitrogen and 4 moles of hydrogen at 300 Kelvin and 1 atmospheric pressure. So, once again you start off with with estimating the total number of moles in the mixture. So, N tot is equal to 8. Now, according to the given problem, the mole fraction of the nitrogen is half. Similarly, the mole fraction of hydrogen is also half. So, I will go ahead and write down and try and evaluate delta G mix. But here there is a little catch over here. I need to know delta G mix per mole of the mixture in units of RT. So, the quantity that I am supposed to find out is actually delta G mix by N tot by RT. This ratio actually means that you are looking at the free energy of mixing per mole of the mixture, and it is not in the units of joules or kilojoules or anything, but it is in the units of RT. So, what I will get on the right hand side, of course, is a dimensionless quantity. And what is this dimensionless quantity? It is a sum of x ln x term for the two components present in the system, and I know that each of the components has a mole fraction of 0.5, and therefore, I find that delta G mix per mole in units of RT would turn out to be minus 0.693. So, as you understand that since I have specified the way you have to express the free energy of mixing, you are getting a dimensionless number. Now, moving ahead, I have a slight variation of this problem over here. I have n moles of nitrogen and 8 minus n moles of hydrogen mixed at the same temperature 300 Kelvin and a total pressure of 1 atmosphere. Now, my question is, for which value of n will delta G mixing have a minimum? Okay. So, in order to understand this, once again I will start by determining the total number of moles, and I find that there are 8 moles of molecules in the ideal gas mixture, and it is also given that the mole fraction of the nitrogen is n by 8, and that of hydrogen obviously is going to be 1 minus the mole fraction of nitrogen. So, for the sake of simplicity, let me put the mole fraction of nitrogen as x, and correspondingly the mole fraction of hydrogen is 1 minus x. Now, I can write down the free energy of mixing very easily now in terms of the mole fractions of its two components, this contribution coming from the nitrogen and this contribution coming from the hydrogen. Now, my question is, what is the value of x, or in other words the value of n, for which delta G mix is going to be a minimum? In order to find that, obviously then you will have to evaluate the quantity the delta G mix at some value of x equal to x tilde, such that this derivative is equal to 0. Okay? This means that to find the minimum, the mathematical exercise that I need to do is, I need to find out the derivative of this quantity shown in the bracket, evaluate it at x tilde and use this to find out x tilde. Okay? So, let us do this exercise. So, in order to do this, what we do is, we try to find out ddx of x ln x plus 1 minus x log of 1 minus x. And it is a little algebra which very easily tells you that now you have to take derivative of x ln x separately from the second term, and if you do the derivative very easily, it turns out that you have a very simple expression over here. Okay. So, the final answer to this derivative is logarithm of x divided by 1 minus x. Now, moving ahead, knowing this, I understand that if there is an extremum in this free energy of mixing, then at x equal to x tilde, log of this quantity must be equal to 0. This means that x tilde divided by 1 minus x tilde must be equal to 1, and that tells me that x tilde must be equal to 0.5. And if x tilde is equal to 0.5, what is n? N is equal to 4. So, I understand that for a binary mixture of two ideal gases, the free energy of mixing has a minimum, or rather an extremum, when it is an equimolar mixture. But I have not still answered the question whether this extremum is a maximum or a minimum? For that, obviously, I have to go back and try and understand the sign of the second derivative of this quantity. And if I want to find out the second derivative of this quantity, I have already taken the first derivative. So, I need to take a derivative of this quantity shown in blue, and that turns out to be this quantity, and this obviously is positive. This means that my second derivative is always positive, and if I evaluate it as x equal to x tilde, where the extremum resides, I find that this is going to be a positive at x tilde equal to 0.5. As a result, what we have learned from here is the free energy of mixing has a minimum for an equimolar mixture of nitrogen and hydrogen. If I plot delta G mixing by nRT as a function of the mole fraction of A, I see that at 0.5 this minimum appears, and the minimum appears for at x equal to 0.5 for any binary mixture of ideal gases. Now, there is a quick recap of the result that we have got earlier. So, at this minimum, the value of whatever is being plotted along the y axis, which is the free energy of mixing per mole of the mixture in the units of RT, that is equal to minus 0.693 as shown here. Now, let me quickly go and ask you this very simple question. What would be the condition where the free energy of mixing exhibits a minimum for a ternary ideal gas mixture at a given temperature T and a total pressure P? Now, what is a ternary ideal gas mixture? Ternary means something that has three components. Okay? So, in this case, I must be having, instead of x1 ln x1 plus x2 ln x2, now I have three terms here involving the mole fractions x1 for component 1, x2 for component 2 and x3 for component 3. But here, just like before, I must be having an additional constraint that x1 plus x2 plus x3 must be equal to 1. Now, what I do is, when I write this down, I understand that there are only two variables which decide the free energy of mixing. These are x1 and x2. Once you have fixed x1 and x2, x3 is automatically fixed by this relationship. Therefore, I now need to bother about two derivatives in this case. First, the derivative of free energy of mixing with respect to x1, and second would be the derivative of the free energy of mixing with respect to x2. And I need to find out those values of x1 and x2 for which these derivatives as shown here will vanish. Now, actually this is very simple to work on. So, you can just find out that the first derivative is nothing but ln x1 by x3, and therefore, under the condition where this derivative is equal to 0, it implies that x1 must be equal to x3. Similarly, for the second component, it implies that x1, x2 must be equal to x3. Therefore, the minimum for the ternary mixture appears when x1 is equal to x2 equal to x3, and you can actually go ahead and show that this indeed is a minimum and not a maximum. Now, if I look at another simple ternary mixture where I have 4 moles of nitrogen, n moles of hydrogen and 8 minus n moles of hydrogen, and ask you to find out the minimum of the free energy per mole in units of RT, what will you do? You will say that the total number of moles in the mixture is 12, and I have the mole fraction of each component as 1/3 n by 12 and 8 minus 8 by 12. And since the free energy minimum would appear for equal mole fractions, then n by 12 must be equal to 1/3, okay? And that means that n must be equal to 4. And when that happens, then I must be having delta G mix by n dot R T, that is equal to minus 1.1. Then if in a trick question somebody asks you what is the value of the free energy of mixing per mole of the mixture, it is not enough to write this result. In that case, you will have to put in the values of R T and give the answer in terms of kilojoules per mole. So, I will stop here, and what I have discussed here is how to use one working formula and adapt it to many different working problems and solve the problem of ideal gas mixtures. Thank you.